Welcome to this module on vector databases. Throughout this module, we will delve deeper into vector databases, which allows us to enhance large language models with additional knowledge. There are two main ways in which large language models can be used. One is through fine-tuning during training, and the other is through the model's inputs. In model training, also known as fine-tuning, we adjust the weights of the model. The more recent methods involves model engineering, also known as the model phase. The other more recent approach involves prompt engineering, where we add information and context to the prompt, and this is done through the inputs. We pass knowledge directly to the model in the prompt and incorporate it as context in the model's responses. Fine-tuning is useful for specialized tasks, while providing context allows for more precision and enables the use of knowledge in the responses. However, OpenAI's GPT-3 model has a limitation in terms of the character length it accepts in the context, which is 4,000 tokens. This isn't very long considering the length of most documents. One solution would be to pass summaries of the documents or break them down into smaller chunks. Anthropic has developed a model called Cloud, which can handle up to 100,000 tokens per context, but this incurs a higher cost and also requires more processing time. Although increasing the context length helps the model acquire more information, new model architectures and solutions are needed to address context-related challenges more effectively. One effective way to pass knowledge to the model is through vector databases. Starting from a large corpus of knowledge, we would break it down into different fragments, transform these into embeddings, and then orderly store them through a semantic index in a vector database. This vector database allows us to perform a semantic search for the most relevant information fragment to answer the user's question. Thanks to this system, the model could utilize relevant knowledge in its responses without the need for a fine-tuning process or an increase in the token capacity that the model accepts in the input. This is why vector databases have gained significant relevance in recent months, with more advanced and efficient vector databases being developed. Initially, we started with traditional databases, which were relational databases queried through SQL. They were designed for structured data and depended on fixed schemas. We then moved towards unstructured databases, the NoSQL databases, which offer greater flexibility in handling unstructured or semi-unstructured data. Finally, in the latest development phase, vector databases were developed. These vector databases provide an optimized solution for managing and querying high-dimensional vector data, for example, data fragments transformed or derived from texts. These types of vectors are in fact what large language models use to work with texts. In this task, we will focus on explaining what vector databases are, as well as their characteristics. Vector databases, also known as similarity search databases or nearest neighbor search databases, are specialized databases designed for efficient storage and querying of vectors. They are particularly beneficial for data development applications. Unlike traditional databases, which are optimized for operations such as index search or structured data query, vector databases focus on the search and retrieval of information based on vector similarity. These databases offer advanced capabilities for working with vector data. They enable operations such as finding elements most similar to a given vector, calculating the distance between vectors, searching for elements that meet specific similarity criteria, or performing range searches. These functionalities are especially useful in applications that require efficient information retrieval based on similar features or attributes. The popularity of vector databases has surged due to the growth of applications using machine learning algorithms and vector-based word representation models known as large language models. These models generate vector representations of data, facilitating similarity comparisons and searches among them. Vector databases provide an optimized environment for storing and querying these vectors. It is also noteworthy that vectors are not only derived from processed text, but any unstructured data, such as images, audios, or videos, can be transformed into vectors through various transformers. Subsequently, these vector databases can be used to search for instance, images similar to each other or audio similar to each other. Regarding the features of vector databases, several points stand out. First, they support vector similarity search, which identifies vectors closest to a specific query vector. According to the similarity metric, this process will yield a list of the most similar vectors. Vector similarity search is beneficial for applications such as image search, natural language processing, recommendation systems, or even anomaly detection. Moreover, vector databases use vector compression techniques to reduce storage space and improve query performance. Another key feature of these databases is their ability to perform an exact or approximate nearest neighbor search, depending on the desired balance between accuracy and speed. Exact nearest neighbor search offers perfect result or similarity, but it can be slow, especially with large datasets. Conversely, approximate nearest neighbor search utilizes a series of algorithms to accelerate the search, potentially at the expense of result accuracy. These databases also support different types of similarity metrics, such as L2 distance or cost of distance. Various similarity metrics can be adapted to different use cases and types of data. Lastly, the distinguishing feature of vector databases is their capacity to handle a range of data sources, such as text, images, audio, or video. These data sources can be transformed into vector embeddings using machine learning models, such as word embeddings, sentence embeddings, or even image embeddings. Now that we have a better understanding of this type of database, our next task will delve into the different vector databases currently available. In this task, we will discuss the most popular vector databases today. Additionally, we will learn about the differences between these databases, libraries for generating vectors, and plugins. We will start with a list of the most commonly used vector databases today, many of which we will cover in this tutorial. One of the most well-known systems is Phase, developed by Meta. This is a library aimed at similarity search and efficient clustering of dense vectors. It allows managing sets of vectors of any size and provides support for evaluation and parameter tuning. Then there is Melvus, an open-source software that allows us to handle large sets of vectors and comes with tools for evaluation and parameter tuning. Additionally, it supports multiple search indexes and has built-in filtering. Another relevant database is Quadrant, which combines a vector similarity search engine with a vector database. This system offers a production-ready service with an easy-to-use API. Elasticsearch is another prominent name in this field. It is a distributed search and analysis engine that, in addition to other features, supports vector fields and provides tools to index and search vectors efficiently. On the other hand, WebAvid is an open-source solution that allows storing objects and vector embeddings. Vespa is a search engine that acts as a vector database and supports vector, lexical, and structured data searches. pgvector is an open-source extension for PostgreSQL, allowing the storage and querying of vectors directly from the PostgreSQL database. Lastly, Pinecone is a vector database specifically designed for machine learning applications. It is based on the Phase library, and it stands out for being fast, scalable, and compatible with different machine learning algorithms. In this task, we'll delve deeper into vector databases like Pinecone. One drawback of using an in-memory vector store is that each time we query our large language model, the entire text must be reprocessed. For smaller documents like a single PDF, this isn't time-consuming. However, when dealing with a dataset of 20 PDFs, each response would necessitate reprocessing all the text, which becomes highly inefficient. A more efficient solution is to employ a cloud-based vector database, which stores all the embeddings and indices, thus significantly speeding up searches. Consequently, when interacting with our assistant, we receive near instantaneous responses. One might wonder, why not utilize a traditional database? The answer lies in their efficiency, or lack thereof. Traditional databases rely on exact matches for queries, which might not yield the desired results. In contrast, a vector database searches for vectors that most closely resemble the user's query, ensuring greater efficiency and accuracy in returned information. Hence, a cloud-based vector database is indispensable for storing our data. Such databases employ an approximate nearest neighbors search, often abbreviated as ANN, renowned for its high performance, accuracy, and speed. The workflow with a vector database typically involves converting data into vectors and establishing a set of indices to facilitate efficient vector searches. When a user submits a query, the system identifies vectors that most closely match based on similarity searches. Subsequently, post-processing enables the large language model to utilize these relevant data segments. A notable vector database solution is Pinecone. Pinecone is an acclaimed choice for large language model vendors, adeptly navigating complexities and high dimensionality associated with vectors. Being cloud-native, Pinecone efficiently manages high-dimensional vector data. It employs an approximate nearest neighbor search, expertly identifying and ranking vector query matches within extensive datasets. As per its official website, Pinecone is user-friendly, fully managed, and highly scalable. Examining Pinecone's features, it boasts rapid and up-to-date vector searches, ensuring minimal query latency even when handling billions of data points. Pinecone's indices are continuously updated, guaranteeing users the most recent information. Additionally, it facilitates filtered vector searches, amalgamating search functions with metadata filters for swifter, more pertinent results. Unlike some standalone vector indices, which demand a comprehensive reindexing to integrate new data, Pinecone supports real-time data amendments without necessitating constant reindexing. Other features include backup capabilities and collections, enabling data preservation and selective index backups. Furthermore, its versatile API caters to a myriad of applications, irrespective of the programming language. From a cost perspective, Pinecone is economical due to its cloud-native design and a pay-as-you-go pricing structure, ensuring users only pay for what they utilize. To explore Pinecone further, let's visit its official website. Navigate to pinecone.io and select Sign up for free to begin using Pinecone at no charge. Various registration methods are available. Once signed up, we can access the Pinecone dashboard. After a brief initialization period, select Create Index to commence index creation. We'll name our index Flowise and proceed with configuration. The dimensions will be contingent on our model of choice. For instance, with the OpenAI model, the dimensions would be set at 1536 using a COSIN metric. However, for different models, consulting the relevant documentation will provide the necessary dimensions. Starting with the complementary starter version, click on Create Index. The subsequent screen displays the created index, which initially contains no vectors. This space is reserved for our vector storage. The interface also presents details like completion status, storage, region, replicas, dimensions, and the search metric, which in this scenario is COSIN based. Armed with a deeper understanding of Pinecone, our next task will involve integrating this vector database into our Flowise project. In this task, we will explain how we can add Pinecone database to store vectors and already processed embeddings. This way, we won't have to pre-process them every time we make a new query to our large language model. If we recall the previous tasks, we had developed a large language model with memory. This model was capable of learning from the information we provided in a PDF. For this, we had added the retrieval quotes chain element in the large language model, in this case GPT 3.5 Turbo. Additionally, we had incorporated in-memory vector store. This design meant that every time we wanted to launch a new query to our model, it was necessary to reprocess the retrieval quotes chain element and regenerate the OpenAI embeddings. This operation is time-consuming, especially because it also involves reprocessing all the information from the PDF. To solve this, we considered creating a new language model, specifically version 4.5. Also, it is essential to replace the in-memory vector store with a vector database, such as Pinecone, that stores the embeddings. The first step is to remove the in-memory vector store. Next, we will go to the vector store section and select Pinecone, specifically the Observe document option. Pinecone offers two tools, one to process documents and another to load already processed indexes or texts. In our case, we will select the second option and proceed to configure it. We will add the PDF file in the document section and the OpenAI embeddings in the embeddings connector. Then we will be asked for connection credentials and indices. To get these credentials, we will go to the Open option, select Create New, and extract the credentials from the Pinecone session. More specifically, we will access the API Keys section to copy the key and name. Once copied, we will paste it in the corresponding place and complete with the environment. Once the credentials are set up, we will need to indicate the name of the indices obtained from Pinecone. In this case, the index is Flowise. Looking at Pinecone, we see that there are no stored vectors. However, after processing the information, this number will change. When making a query to the model, it will execute the whole process and generate the indices stored in Pinecone. If we launch a question, we will observe that it takes a few minutes to answer. This delay is because it processes the PDF, generates the embeddings, stores them in Pinecone, and then accesses the Pinecone database to find the most appropriate answers. We can verify that the model responds adequately. Also, when checking Pinecone, we notice that we have gone from having 0 stored vectors to 16. This indicates that the PDF information is already stored in Pinecone. Therefore, unless the PDF undergoes modifications, it will not be necessary to process it again. In this task, we will learn how to generate a chat flow that loads existing embeddings, using this information to respond to users. In the previous task, we had added Pinecone's vector store. This allowed the information from a PDF to be broken down into different fragments, and with OpenAI embeddings, the embeddings would be generated. This, in turn, would be stored in Pinecone's vector store. However, if we wanted to take this workflow to production and we know that the embeddings won't change, for example, the information from the PDF won't be modified, the most logical step would be to simply load the existing embeddings. In this way, we would reduce latency when responding to the user with relevant information. To do this, we need to slightly modify the chat flow. The first thing we will do is remove the PDF file and the text splitter. It won't be necessary to provide the original information since the already processed embeddings will be loaded directly. Therefore, we select them and proceed to delete them. After deleting them, we will also modify the Pinecone element. First, we remove the connection and delete the Pinecone element. If we go to the vector store section and search for Pinecone, we will see that there are two different elements: Pinecone observed document, which allows introducing or storing embeddings in Pinecone, and Pinecone load existing index, which will allow us to load already existing embeddings. Instead of regenerating the documents, we will load those already processed and stored in embeddings format. We add this last element and remove the observed document one. It is necessary to provide the previous credentials. If we recall, to obtain the credentials, we must go to API Keys and copy the environment. Additionally, we need to specify the index name, which in our case is Flowise. If we go to the index section, we see it is the only one we have, and it contains 16 stored vectors. We proceed to reconnect the embeddings, as they need to be processed so that the large language model can use the information. We add the OpenAI embeddings component and connect its output to the vector store retriever section. We save the workflow and test it. We erase the history and make a query about what GPT-4All is. Since we no longer have access to the PDF, the only option is to load the information from the embeddings. We see that the answer is based on the information we previously loaded from the PDF. This validates the access to Pinecone's database works and that we can extract the information we need. This would be the process we would take to production if the information the model is trained on doesn't vary. By directly loading the indices, we avoid the pre-processing step and thus significantly reduce the response latency to the user.